Hello and welcome. I'm Dylan, and today we have a short video that will cover the basics of Thevenin's theorem and how it is utilised in circuit analysis. So what exactly is Thevenin's theorem? The theorem states that any combination of power sources and resistances can be reduced to a simple circuit consisting of one voltage source and one resistor. By implementing this theory, it allows us to reduce incredibly complex portions of networks into a much simpler and easy to understand circuit. The example shows how the circuit would look after it has been simplified, in which the new values are known as the Thevenin equivalent resistance and voltage. There are essentially 5 steps to convert a circuit into its Thevenin equivalent. Step 1. We establish which part of the network we wish to convert. Step 2. We mark the terminals across the load element and remove it. Step 3. We remove all the power sources and calculate the Thevenin resistance, coming from right to left. Step 4. We then re-enable the power sources and calculate the voltage. And lastly, we simply redraw the circuit. These steps may seem pretty vague and confusing at first. However, we will now go through a simple example to reinforce these ideas. In this example, our load element will be resistor 3. Firstly, we establish what we want to convert. In this case, it is the entire system. We then remove resistor 3 as it is specified as the load element and label A and B across its path. Step 3. We remove the power source and calculate the resistance coming from right to left. In this example, we have R4 in series with the 2 parallel resistors R1 and R2. We then get the following equations, resulting in a Thevenin resistance of 140.91 ohms. Step 4. We then re-enable the power supply and use voltage divider rule to find the voltage across R2. As R4 is in an open circuit, no current is flowing in that path and thus can be excluded. Parallel paths exhibit the same voltage and thus the voltage across R2 becomes the Thevenin's equivalent voltage. Through calculations, we then end up with 13.64 volts as our Thevenin voltage. Lastly, we redraw the circuit in a simplified manner, as shown, with the new calculated Thevenin equivalent values. Thank you for watching, and I hope that you have learnt a little bit more about Thevenin's theorem and how to utilise it.